All right, welcome back again, everybody. Today we're finally going to get to do some calculus with polar curves and polar equations and so on. The last section, we developed the entire polar coordinate system and how to sketch curves and things in that system. Now we're actually going to do some calculus. So this is kind of a fun section. It's always good when you get to do some calculus, right? So let me pull up the slides and let's begin. The good news is this one is not as long as the other one, so I know I like to mention that. A lot of times when you have to set up a theory, it takes longer. Now we're just going to be kind of using the theory. So we're going to talk about parameterization, then we're going to talk about how to find tangents in polar coordinates, area in polar coordinates, and then arc length in polar coordinates. So it's very similar to what we saw when we just developed the calculus for parametric equations, right? Okay, here we go. We're actually going to use those formulas, in fact, because a polar parameterization is a parameterization. It's just a kind of parameterization. Anyway, okay, so let's say that we have a radius function f of theta, and it's given in polar coordinates. So you put in an angle and you get out a radius. Then what we can do is we can write x equals r cosine theta, but because r is a function of theta, we can replace r with f of theta. Sometimes we'll even just call it r of theta. That's very common, which I do a few times on here. So x is f of theta cosine theta, and y is f of theta sine theta. So in other words, we can describe x and y by these parametric equations. These are our parametric equations. And now we can apply the general theory that we developed in section 10.1 and get all of these formulas, just now they're in terms of polar coordinates. All right, so here we go. Given these parametric equations, we can use the general formula that we derived for tangents from section 10.1 to conclude that this is the slope of the tangent line. There you go. That's the slope of the tangent line. This one, yeah, I'm not going to go through the derivation, but you're more than welcome to do so. It's basically the same thing that we saw before, so it's not worth repeating. But if you look back at section 10.1, you'll see how to get this formula. But that is the formula right here. All right, now we're going to use it. So let's say we have this polar equation. Let's find the slope of the tangent line when theta equals pi over 3. And remember, this equation right here is given in polar form, and so it's describing a polar curve. Maybe you might recall that this is actually that this is that cardioid, right? This is that cardioid, which looks like this. Maybe I can kind of. It's hard to draw in one smooth motion. That's a little better. So there's the cardioid. That's what this is actually describing. And what we want to know is we want to know what's the slope of the tangent line when the angle is pi over 3. So if the angle is pi over 3, that's about here. Actually, I should have made that green. Let me try that again. Right? So this is the angle pi over 3. And what we want to know is what's the slope of this line. Question mark. What's the slope of that line? That's really all we want to know. Like I mentioned back in section 10.1, even though we're describing these curves in a different way, we want to be able to do calculus with them, and we want to be able to find these results, these calculus results. So that's what we're doing here. We're just going to use the formula. We literally just plug in our information to the formula, and that's about it. So here is the actual function. So you could think of this as, let me use blue. You could think of this as r of theta equals 1 plus sine theta, or you could think of it as f of theta, whichever you want to call it. Right? And then you just plug in the values. So what is the derivative? This is dr d theta times sine theta. This is r times cosine theta, yada, 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 et cetera, et cetera, et cetera. Go through the algebra, and then you end up with this. Okay, so the good news is that this formula right here gives you the slope of the tangent line at any point on the curve, as long as sine theta is not equal to 0, right? Yeah, as long as sine theta is not equal to 0. Because then what you'll have is you'll have a vertical tangent. So just like before, just like in section 10.1, If you want to know where the tangent line is horizontal, you set the numerator equal to 0, or really just the derivative equal to 0. And if you want to know where the tangent line is vertical, you would set denominator is equal to 0. And that's how you get it. All right, now we want to know the slope of the tangent line at this particular angle, so we're going to take this formula and plug pi over 3 into it. So when we evaluate this formula at pi over 3, we get all of this, and then we get this. Okay, that's the simplification. So the slope of that line that I sketched, oops, right here, the slope of this line is what we just calculated, 1 plus root 3 over negative 3. That's the slope of that line. Double check that I wrote the right one. Yeah, that's right. All right, so that's how you find tangents. You just use that same tangent formula. Okay, now let's talk about areas. And this one I just think is it's just such a beautiful construction. I just love how this is constructed. This is one of the reasons that I emphasize the mechanics of the Riemann integral so much in Calc 1 and in this class, because when you understand how the integral is actually working and what the integral is actually doing for us and what the integral is actually telling us, you can do all these amazing things with it. It just boils down to figuring out what you want to measure. And once you figure out what you want to measure, you can integrate and get all of this cool information. So we explored the mechanics of the Riemann integral extensively before. Recall it again, because we're going to extend it into this new coordinate system. So if you remember, we developed the Riemann integral by cutting up this region, cutting up this subinterval, cutting up this interval into these subintervals, and then constructing all of these approximating rectangles. And that's what this piece is inside the sum. You're getting the area of all these rectangles, and then you're adding them up, and that gives you a rough approximation of the area under that curve, right? Then you take the limit as the thickness goes to 0. So you basically let the rectangles shrink in size until they're very, very thin, infinitesimally thin. And then in the limit, you get the exact area, and that is the definite Riemann integral. So that gives you the exact area under this curve. So how do we extend this idea to curves that are described by polar coordinates? So here, remember, we had x and we had f of x. This is a Cartesian representation of a curve. And what we did was we added up the areas of a bunch of rectangles. So how do we generalize this or extend this to a region that's described by polar coordinates? And what I want you to do is just think about it for a minute. So take a minute and think how you would do this if you had to. All right, so this construction is very beautiful, so I hope you appreciate it. Here's how we do it. Remember that the area of a circular sector with central angle theta is given by this formula right here. This is a formula that you learn in pre-calculus or trigonometry. It's just the area of a circular sector or the area of a wedge. So what we're going to do is, instead of using rectangles like we did in the rectangular coordinate system, we're going to use these wedges. Since our coordinate system is radial in nature, it's circular and radially described. So what we want to do is we're just going to use these circular sectors to approximate our region, and then add up all of the areas of those circular sectors. So here we go. Let's say this is the region that we want to find the area for. And this region is given by a polar function where r is a function of theta. And let's say we want to find the area of this region between the rays theta equals a and theta equals b. All right, so we want to find this area. We're also going to assume that we're not wrapping around the pole more than once. We're just going to assume that this area doesn't come back and cover itself again. In those instances, what you have to do is you have to split it up into multiple integrals, but we're not going to look at that right now. We're just developing. So this is the angle, I'm sorry. Oh yeah, this is the angle A, this is the angle B, and our region for now is trapped between these two rays. What's the area of that region? That's the question. So here's the clever part. What we're going to do is we're going to divide the interval a to b into subintervals theta sub I minus 1 to theta sub I of length delta theta, and we're going to approximate this region with circular sectors. That's a circular sector. So if we can find the area of that circular sector at each point, or sorry, at each subinterval, then we can get a good approximation of the area, right? So for one, remember that the interval a to b, that is this interval right to here that I drew with that red arrow. That's the interval a to b. And so what we're going to do is we're going to cut it up into a bunch of subintervals like so. And in each one of those subintervals, we're going to choose a sample point. We're going to choose a sample point, and that sample point is theta sub I star. And that sample point is exactly where we're going to evaluate our polar function. We're going to plug theta sub I star, that sample point, into our radius function, and it's going to give us, let me use this here, it's going to give us the length of this ray right here. The length of that, that line segment, really I should say, that line segment. That line segment comes in contact with our polar curve, and that gives us the end of our circular sector. There we go. That's what it is. Literally what it is. So now we have the sample point, we have the radius associated with our circular sector, and this width. So the change in this angle, that's delta theta. Delta theta. We're going to use equal length subintervals, by the way. Now, remember, this is the formula for the area of a circular sector. So the area of this circular sector that I depicted here is given by this formula right here. 1/2 r of I sub I theta, r of theta sub I star squared times delta theta. Why is it delta theta? Because delta theta is the size of this angle. So delta theta is the size of this angle right here. That's delta theta. That's it right there. What is the radius associated here? The radius is given by our radius function. And then here we're just using the formula. So what that does is that gives us the area of this circular sector. And we're going to do that at every single one of the sample points and for every single one of these circular sectors. And we're going to add them all up. We're going to add them all up. And in doing so, that gives us a good approximation of the exact area. Maybe now you can see what's going to happen next. Use the good old limit operator, take the limit as n goes to infinity or as delta theta goes to 0, and we get the exact area. Voila. There it is. So this is the area formula for a polar region. So rather than using f of x delta x, or I'm sorry, f of x dx like we did in the Cartesian form, this is what we're going to use instead. So we've got to use 1/2 r theta squared d theta. So everything's in terms of thetas and r's. And it's just really, just a really beautiful construction, I think. And it's again, it's one of those instances or instantiations of the Riesz representation theorem, because you basically want to measure the area of this region. You just have to figure out how you're actually going to measure the area of that region. And for our purposes, this is the function that we needed to add up to get the area. That's the creative part. So cool. Okay, now let's use it. So let's try this. Find the area enclosed by one loop of the four-leaved rows given by r theta equals cosine 2 theta. I took the liberty of including the picture here. We want to find the area of this loop. And I gave you these two bounding rays as well, just to save a bit of time. So I want you to think about how you would do this one first, and you're going to try this one on your own before we do it, but think about what you would do first. All right, now say something out loud about what you would do first. How would you approach this in the beginning? All right, now try to work it out on your own. Remember, you've got the formula here. Start with the formula and see if you can find the exact area. All right, now let's do it together. Okay, so fun stuff. So using the graph, we can see that the region enclosed is between these two rays just from the picture. Some of you might have been wondering, hey, what if you don't have the graph? Or hey, what if I don't know how to graph that yet? Or how would I be able to know the bounds of integration? Well, algebraically, what you would do is remember that one loop is occurring when, let me erase some of this. One loop is occurring when the curve returns to the pole. So here's one loop. So if you wanted to know what one loop is, or where one loop is, you have to solve the polar equation r of theta equals 0. And that's what I'm showing here at the bottom. So you would say, well, set r of theta equal to 0 and solve for theta. That means cosine 2 theta is equal to 0, which means 2 theta equals pi over 2, which means theta equals pi over 4. And then there are multiple uh, multiple repeats, right? So normally you could say, oh, this would be plus 2k pi, divide by 2, you get plus k pi, and so on and so on. So you can find all these solutions. And pi over 4 is the first solution. And then the reason I picked negative pi over 4 is just because it'll be easier to integrate between those two rather than integrate between these two up here. Because you could also integrate between pi over 4 and 3 pi over 4, and you would get the same result. But there's some nice symmetry involved here, and it's going to be handy to exploit that symmetry in this case. All right, so that's how you would do it algebraically. Now, here's how you do the actual calculation. Here's our formula for finding that polar area. We're integrating from negative pi over 4 to pi over 4. This is me just plugging in r of theta. Now, we know how to deal with this from earlier on in the course, right? We basically got cosine squared, so we use a power reducing identity. So, but before I even use the power reducing identity, notice what I'm doing here. I'm going to exploit the symmetry of my region, and instead of integrating from negative pi over 4 to pi over 4, I'm going to integrate from 0 to pi over 4 and double the result. Double the result because there's symmetry there. The 1/2 I just pulled out by linearity, and now I've got cosine squared. How do I deal with that? I use the power reducing formula, which leaves me with this. Now we've got a simple integral, a simple trigonometric integral to evaluate. Do the antiderivative, you get this, and fundamental theorem part 2 gives us that the result is pi over 8. Cool stuff. So going back to the picture, what we just found out is that the area of this region is pi over 8. So for example, if you wanted to know the area of the entire rows, you would just multiply that by 4. The area of the entire rows is 4 times pi over 8, or pi over 2. There you go. Cool stuff, cool stuff. Okay, now where was I? This one. Okay, now let's try this one. Let's try this one. This one's a little bit tricky, but I want you to try to think about it on your own too. So let's find the area of the region that lies inside the circle 3 sine theta. So that's this circle, but outside the cardioid given by 1 plus sine theta. So outside of this. All right, so we want to find the area of this region right here. All right, within that region. Maybe you might see how we can actually go about this. If we want to find the area of a region between two curves, we're going to use that same formula that we learned back in Calc 1 to find the area between two curves, right? We just need to find the outer curve or the upper curve and subtract from the bottom curve or the inner curve. So basically we can see that our integral is going to be this minus this, or those are, I should say, this is the upper function and this is the lower function. That's one thing we're going to do. So let me pause there. I guess I've already kind of given enough. I want you to think about it first. So think about how you would start this and say something out loud to yourself about how you would start this. All right, now try to work it out on your own. I'll give you a little bit of a hint that can save you some work. Notice that these two regions are, I'll just say, shaded a different color. Think about that. All right, now let's try to work it out together. Um, for one, we would need to find the bounds of integration. In this case, they're actually given to us, these two rays. So the bounds of integration are going to be from pi over 6 to 5 pi over 6. Again, if you didn't know that from, like let's say you didn't have the graph, how would you find that information out? You would set those two functions equal to each other and solve for theta, which I believe I do here. Yeah, set those two functions equal to each other and then solve for theta. So when you simplify this, you'll get this, sine of theta equals 1/2, which means it's got to be those 2 points right there, or those two angles right there. So those are the bounds of integration. Now we also saw that this is the outer function and this is the inner function. So quite literally what we're going to do is we're going to do the area of the circle minus the area of the cardioid between those two regions. That's all we're going to do. After that, you've just got a basic integral calculation. So let's look at what we've got here. I exploited symmetry here. I can tell now just by looking at it. So to go from this step to this step, let me walk through it piece by piece. This just becomes this by squaring. But notice here I was integrating from pi over 6 to 5 pi over 6. Now I'm only integrating from pi over 6 to pi over 2, but I'm doubling the result. And I'm doing that for both integrals. So just doubling the result to save myself a little bit of a headache. I also FOILed this out to get this as my integrand for the right integral. Okay, now at this point, it's a lot of algebraic simplification. And I think, wait a second. I think I have a typo here. Wait, do I have a typo here? Oh, no, I see what I did. Here. I actually combined these two integrals to get to this step. That's what I did there. Yeah, because you see we've got a sine squared theta and we've got 9 sine squared theta. We're taking away this one, so we get 8 sine squared theta. That's what it is. Yep, that's what it is. This 2, when you distribute it to these 1/2s, that's what's getting rid of the 1/2s. So there's no more 1/2s after this is distributed. And then I kind of combined things. To be honest, I could have combined things at the very beginning. I didn't need to write this as 2 separate integrals, but that's okay. Now to go through some algebraic simplification, and you get this. Looks like what I did here was I used the power reducing identity. And now I've got a more simple integral that I can evaluate in the usual ways. FTC2, apply it at those endpoints, and we get pi. So, maybe surprisingly, the area contained in this region is area pi, or it has pi units. Ah, cool stuff, huh? Cool stuff. All right, so that's it for area. Now let's take a look at arc length. Plowing right through here, okay? So remember from section 10.1 that we found this general formula for the arc length of a curve described parametrically, right? So if you've got a curve described with these parametric equations, x equals f of t, y equals g of t, then you get this general formula for that length between alpha and beta. Well, remember our parametric equations are these, right? So we parameterized everything in terms of polar coordinates. So this is x and this is y. We also computed earlier, or at least it was computed earlier, that dx d theta is that and dy d theta is this. So now using this general formula, we can plug in what we know and simplify to get the formula for polar coordinates. Here's the full calculation. I won't go into the nitty-gritty details, but if you would like to, you're more than welcome to. It really just boils down to a lot of algebra. Dx d theta is this, dy d theta is this. Then since you're squaring these things, you're going to have to FOIL everything out. You get a big mess, but the mess cleans up rather nicely. Then you can factor some things out, and these are both equal to 1. Looks kind of like a sad face. I shouldn't say that. This is equal to 1. This is equal to 1 happy face. So those get wiped out, and then all you're left with is this. So this, this expression here, this pair of terms, becomes this pair of terms. And so our formula for the arc length given in polar coordinates is this. So assuming that our radius function, the derivative of our radius function is continuous, then we can write the arc length like so. Like so. And this is just really, really cool. Like, it's really just amazing how much these formulas are related and how they're all so similar. You don't even really need to memorize all of them if you can see the structure, right? So let me go back to this formula. AB. This is the one that you get back in Calc 1, or like we talked about at the very, very beginning of this course. Or I'm sorry, section 8.1. I'll just say section 8.1, right? Remember you had this, and it was dy dx squared dx. This was the equation for a curve that's given in Cartesian coordinates. And now this is the equation, actually, you know, yeah, this is the equation of a curve given in polar coordinates. So look at the similarities in structure. Look at the similarities. dy dx, so it's literally derivative of the, you know, dy versus dx. This is dr versus d theta, right? But here, y is a function of x, and here r is a function of theta. So these two terms are analogous to one another. They're the derivative of your function. And then here you've got 1, but here you've got r squared. This r squared is coming from the radial nature of our function, the radial nature of the function. That's why here, this was just 1, because dx over dx is 1. Here we're getting r squared because there's a scalar involved that's related to the radius of this curve, just like so, right? And then even just more generally, like we got in section 10.1, the general formula is just alpha, beta, and then you had dx dt squared, dy dt squared, dt. So all three of these formulas, they're all just so intimately related. It's really, really cute. Okay, now let's use it. So I want you to try this one. You've got the formula right here. Now it's kind of hidden in the mess. You've got the formula right there. Try to find the length of the polar curve given by this polar equation in between these angles right here. This one I'm going to throw right into your hands. Use the formula, try to calculate it yourself, and we'll do it together in just a moment. All right, now let's do it together. Pretty simple calculations. We've got the formula, we've got the bounds. We just have to dive in, cross our fingers, hold our breath maybe, and just walk through comfortably. Here we go. Here's the formula. This is r squared. This is dr d theta squared. When we simplify this, we get this. Sine squared plus cosine squared is 1. So our integral becomes very, very nice. Very, very nice. It becomes square root of 36, which is just 6. And then we're just adding up d theta at that point. So we get 6 theta between pi over 3 and 0, which becomes 2 pi. So that's the length. The length is 2 pi. Because it's basically a unit circle that's been shifted. Cool stuff. Wait, is the unit circle? Hold on, this is the length. No, I shouldn't say, that's not a unit circle. Can't be a unit circle. This number is way too big for it to be a unit circle. Yeah, that's right. It's 2 pi, but we're not integrating around the whole thing. Yeah, we're only integrating from 0 to pi over 3, not the entire circle. All right. On that note, let's play. So that's it for this one. I'm happy it wasn't so long. Once again, I'll try not to ramble too long, but thank you again for paying attention and watching the lectures. I look forward to working with you. This is actually the end of chapter 10, if I'm not mistaken. Let me double check. Oop. Let me double check. Yes, yeah, that's it. This is the end for chapter 10. Now we're going to move into chapter 11, which is where we get all the really amazing stuff. So I'm really, really excited to get to chapter 11. All right, now I'll stop rambling. Thank you again, and I'll see you next time.